Yes, okay. Welcome everyone to the IODP Expedition 389 information webinar. And thanks very much for connecting with us to learn more about our expedition to core the drowned reefs around Hawaii. My name is David McEnroy. I'm your webinar host, as well as the science manager for the ECORD Science Operator, or ESO. And I lead the group that's responsible for implementing this expedition, and will do so under the auspices of the International Ocean Discovery Programme. So joining me for this webinar are the expedition co-chief scientists, Professor Jodie Webster from the University of Sydney in Australia, and Professor Christina Ravello from the University of California, Santa Cruz. And I'm also joined here by our expedition project manager, Hannah Grant, also from the ECORD Science Operator. So we're all very pleased to have this opportunity to talk to you about the scientific and technical aspects of this expedition, and hopefully we can persuade you all to apply to join the science party. So just before we start, just please note that this webinar has been recorded, and it will include a record of any questions and answers and any chat conversations that we have, and eventually the video and the transcripts will be made public. Okay, let's get started then. So in a few moments, I will ask Jodie and Christina to take over and explain the scientific objectives behind this expedition. After they've finished, Hannah will explain how this expedition will be implemented. Some of you no doubt have IODP experience, perhaps on the JOIDES resolution or maybe the CHIKU, but I'm also pretty sure that many of you will never have participated in IODP before. So this expedition is what is called an IODP mission-specific platform expedition. And Hannah will talk about what that means shortly, because there are some significant differences between this type of operation and the other IODP expeditions that everybody should be aware of. I will then cover the application process and some of the steps that will take place after you apply. And then all going to plan, we should have about 15 to 20 minutes for questions at the end. We'll try not to go over the hour, but we can do so if there are lots of questions coming in. Of course, it's fine for you to leave the webinar at any point. You won't interrupt any of the proceedings. Finally then, during the webinar, please, if you can, register any questions that you might have using the Q&A window. Please try not to use the chat function for questions. It's just much easier for the panel if we can view one window for questions rather than two windows. So please, Q&A window only for questions if you can. That would be appreciated. We'll save all the questions until the end, and we'll try and answer as many as we can. Okay, so we'll move on now to the scientific objectives. So I'll bring Jodie and Christina's presentation online to start the co-chief science presentation. Just stand by a second. Jodie, do you want to go ahead and share your screen?
Yes, we'll do. Thanks,
yeah,
David.
Yeah, over to you, Jodie. Thank you.
All right, just give me 1 minute here. Right. All right. Okay, everyone see that okay? Yep. All right. Well, thank you, everybody. It's a pleasure to be here and introduce the science. And as David said, my name's Jodie Webster, and Christina Ravello is the other co-chief. But kind of launching right in, the objective of this expedition is to recover an incredible suite of fossil coral reef cores from the flanks of the Big Island of Hawaii. And in this image, you can see one of these 3D multi-beam images of the flanks, and essentially as a series of almost like bathtub rings around the Big Island, as we'll see as a result of rapid subsidence over hundreds of thousands of years. There's this beautiful sequence of coral reefs that are preserved down to about 1,500 meters, which are the target of our IODP expedition. And the goal is to use a seabed rock drill of some description to sample these structures at depth. And this, we think, will allow us to recover a really unique sequence of fossil reef archives back to at least 500,000 years through much of these glacial interglacial cycles. And then really there's four main objectives. Firstly, define the nature of sea level change in this part of the world over the last 500,000 years or so. Reconstruct paleo environmental variability over that same period, and really try and establish and look at the relationship between the mean climate state and high frequency climate variability, such as seasonal into annual, which Christine will talk about a little bit later. Looking at the sort of geologic, biologic response of coral reefs to abrupt sea level change and climate changes, and also try to understand and constrain subsidence and the volcanic history. So four main objectives. This is a slide that I like to show my first year students, which I think nicely illustrates how excellent corals and fossil coral reefs are at firstly reconstructing sea level changes, in part because we can date them with a range of different techniques, C14 and uranium thorium isotopes in this case, back to the 500,000 years. And of course, from the paleoclimate aspects, they produce these really excellent annual and interannual growth bands, and we can look at a whole range of geochemical proxies, and there's a few listed there, but many others now that we can use to reconstruct a whole range of different sorts of parameters. On to sea level, and a sort of real focus is to, as I said, reconstruct and produce more accurate records that go back from different periods. You would have all seen diagrams like this. This is from the IPCC, which basically looks at different sea level projections out to 2300 on the basis of different RCP represented concentration pathway scenarios, either 2.6 or 8.5 at the upper end. And of course, there's taking it at the upper end, there's significant uncertainty around the rate and magnitude of sea level rises, and that we might actually see. And in part, that goes to our lack of understanding still of some of the major processes involved in ice sheet dynamics, ice sheet cliff stability, ice sheet instability, and so on. And one of the ways that we can hopefully improve this is by going to periods in the geologic past where they're undergoing major ice sheet decay and collapse to reconstruct more accurate records of sea level. And the drowned reefs are part of this. And so this is part of a longer term plan for IODP that has been working on in various iterations. Basically, this idea of looking at both the Arctic and Antarctic so-called proximal records of ice sheet decay and growth, as also looking at the tropics as so-called far field sites to reconstruct new records of sea level change. And Expedition 310 Tahiti was the first part of, or the first MSP to look at this, and really gave a much better record of sea level change from about 16 to 10,000 years. The next expedition was the Great Barrier Reef, Expedition 325, and it really gave a much more detailed view of the last 30,000 years. And the innovation for Hawaii is to take this record back and particularly sample, as we'll see, different periods of Earth history. And this is a diagram here. There's been a bunch of recent reviews over the last 5 to 10 years or so, pulling together a range of different sea level records, both corals and other records, for example, from the Red Sea and so on. This is Walbreck and Elko Rolling. And these red dots, for example, in this diagram represent the records of from fossil reefs. And what you see is that there's in many cases, a clear bias towards and relatively few records over this period. And many of these records actually come from either tectonically uplifted regions, and there's issues with sufficient data coverage, issues of diagenesis. There's a lack of sort of temporal coverage past much, part of the deglaciation, and certainly we know more about stage 5E, 125,000 years, and some sort of spots in between. And in many cases, the records that we have are quite compressed stratigraphically, in part because of their tectonic sort of setting. And so you really need to go to areas that are rapidly producing accommodation space through subsidence. And that's really where Hawaii comes in, because of the loading of the volcanic edifice over time. This has produced very rapid and well-behaved or continuous subsidence in the order of 2 to 3 millimeters per year. And this has produced this sequence of reefs down to about 1,500 meters that get increasingly older as we go deeper. And so there's been a wealth of work that's been done over the last several decades, and this has gone into the development of the proposal. And I guess the key point there, we can get back at these different levels, the interglacials, the interstadials and stadials, the glacial maxima, and part of the deglaciations in each of these major glacial interglacials. And this is an attempt to try and show that here in this conceptual figure, where in this figure we have depth, time along the top axis here. And in this case, this represents the basement substrate rapidly subsiding. And that relationship between the blue line, which represents our eustatic sea level, or in this case, relative sea level at this place, that relationship, depending on whether it outstrips or goes too fast for the reef to grow, will produce a stratigraphic sequence that could be a combination of shallow, possible short exposure, and so on, till the point where we get the rapid deglaciation, where we then produce reef drowning and then backstepping and producing the next system. And this was sort of a model that would then produce a potential sort of stratigraphy that we see there. And of course, as part of this process, we tried to pull together as much of this data to sort of test and look at this. And this is another sequence showing again where much of the work that we've done, a lot of it's been concentrated so far as part of the site survey, if you will, on the two shallowest reefs, the so-called 150-meter reef, or H1, H2, and the Hawaii 1, Hawaii 2. This is sort of nomenclature that we use, Hawaii 8 that you can see here. But a lot of work's been done on these two shallowest reefs, in part because we have, we're able to access some of that material. And what we're able to show quite clearly is that this H1 reef clearly drowned as a result of rapid sea level rise during the last deglaciation. And also, this is supported by uranium series dating evidence to suggest that this reef here drowned during the penultimate deglaciation. So it sets up this shows this sensitivity. Just to give you a sense of what these things look like, this is a cross-section of one of these multi-beam maps. What we find is that they're not, in many cases, just one reef feature, but actually composite structures. In this case, this is a reef 1, a reef 2, they're patch reef sorts of features. And you can see the depths here ranging from about 150 meters in this case to about 100 meters. This is the shallowest reef. And this is sort of a cross-section. This was sampled using the Mbari ROV. The Tiburon, you can see a suite of sort of images looking of showing you what the seabed looks like in these areas. You can see the manipulator here sampling the reef, and this is a sort of example of the sort of fossil coral algal material that we see. Here we have the massive parietes capped by thick crusts of coralline algae with a range of shallow to intermediate to deep forms, building up this sequence and drowning sequence that we've been able to establish. And there's a lot on this figure, but this is basically just sort of summarizing it at that stage. There's been more sea level records since. This is the Barbados record, Sunda Shelf record, the GISP2 ice core record through here. And these red dots represent the dates of the fossil corals that were taken from the top of the structures. Shallow water corals that in this case, and then we have deeper water algae representing the subsidence path as the drowned reef continues into the deep as sea level rises in that direction. And so this drowned reef crest represents the top of the sequence. And subsequent to that, of course, we've had the work done by Deschamps as part of Expedition 310, better constraining now meltwater pulse 1A, which is consistent with actually what we see at Hawaii. And of course, the Yokoyama Expedition 325 data, which gives a much better view of the LGM. And so just to kind of give you the sorts of the sequence of events, this is that same diagram, but sort of broken down into a series of stages that show that the sequence from shallow reef growth through to this whole range of intermediate to deep open platform and much deeper sequences. You can see this range of corals to algae and microbialite sediments down to hemipelagics. And that sort of, allows us to think about drowning, the rate and nature of community changes, the environmental thresholds, and so on. And we see this same sequence in the successive, deeper reefs. We've followed up a little bit of additional work, following up that work that we did in the early 2000s. In this case, rather than an ROV, we used a human underwater vehicles. In this case, this is divers on rebreather units going down there with hammers and chisels, breaking material off from the top of the sequence. But again, it sort of confirms that picture of significant reef drowning, coincident with abrupt, rapid ice sheet collapse associated with and sea level rise associated with meltwater pulse 1A. And again, that's but really, just at this stage, we are literally just scratching the surface. So that the next step is to try and look at obviously recovering cores from beneath these structures. And this sort of sums up, the sort of situation between these two reefs, H1 and H2. Again, the data isn't quite as clear for H2, but again, it's consistent with this pattern of drowning during the penultimate deglaciation. And again, that's the surface. We have some indications, firstly from computer models as to what we might expect from drilling through these structures, but also some empirical evidence, which I think is quite exciting. So this is work done in collaboration with Laura Wallace, who's helped develop these quite simple sort of 1D models, which attempts to feed this model with a range of different subsidence, sea level, growth sorts of parameters to try and help us think about and make a predictive statement of what we might see. In this case, a whole series of reef stack that might be 100 to 150 meters thick. But it gets a complicated reef sequence, not just one sequence, but a sequence of growth, short-term exposure, growth again and again and again, followed by a final drowning of this structure during the major deglaciation. And that's that sort of setting. Now, the sort of proof of concept, I guess, if you will, comes from some of the sites where we can, in fact, see a cross-section through the reef sections. In some of these areas on one of the this northeastern side, a place called Kohala, where we've done significant work with an ROV. Here you actually have a plunge pool system. In this case, the reef is actually cut by submarine action, cutting into the outcrop. So we essentially have a cross section through the reef section, and we can see these beautiful sequence up the section of massive corals in situ, beautiful variations in framework, a whole really interesting sequence, and a nice indication of what we expect to see when we drill through some of these structures. And you can see the massive parietes there. Here's the actual manipulator breaking off one of these corals at about 1,000 meters, which consequently gave robust closed system uranium thorium ages that confirm that this part of the reef sequence is actually marine isotope stage 11, about 380,000 years. And here's a kind of a picture of that sort of model or the stratigraphy. And again, you can see these massive corals here. And as Christina will explain in a minute, this goes to what we think we can get out of these reef records with respect to really reconstructing excellent records of paleoclimate variability. But I'll introduce Christina now, who'll sort of then talk about some of these aspects.
Thanks, Jody. Yeah, so like Jody said, this is these gave us a tremendous opportunity for sort of proof of concept that we can get paleoclimate data from the internal part of these reefs, if we could drill through them. So this kind of opportunity of these incised reefs gave us these samples of massive corals at the bottom of these plunge pools. And if I'm going to talk a little bit about what we think we can do with these, if you could go to the next slide, Jody. So just backing up a second and reminding everybody about the sort of mean state or background state of climate during this period of time that we think we're going to be able to sample. So the upper plot just shows the sea level curve and kind of where the reef systems, the reefs that we think that we're going to drill through land on in terms of past insulation changes, past sea level changes, and past climate changes and CO2 changes. So we're essentially going to be able to get windows of high resolution climate variability during periods of different mean states, and as shown here. So on the next slide, I just want to make the point that these, in the big picture, the samples are smack in the middle of the North Pacific subtropical gyre, but they're at this transition. In the upper left is the chlorophyll record. B shows the geostrophic, shows something about the geostrophic recirculation. So, and then C and D are both sort of multivariate seascapes defined by temperature, chlorophyll, and a number of parameters. And this just shows, in this particular paper, what they talk about is how there's been a recent expansion of the subtropical gyre, and Hawaii kind of sits at this very sensitive place where we can see early indications of the expansion of the subtropical gyre in the last decades. So this is so Hawaii is a really important place for being able to look at changes in the hydrography and the mean state of the subtropical gyre, and also sort of on long time scales and short time scales as well. And the next plot will make the next slide sort of illustrates possible impact that El Nino can have on Hawaii. So rather than go through the slide in general, just if you look at C, that's the Central Pacific. Those are Central Pacific El Ninos and what the anomaly during a Central Pacific El Nino looks like relative to the climatology. You do get an anomaly there. So Hawaii is sensitive to El Nino, so it should be sensitive to what's going on in not just global climate, but also regional climate in the tropics. So there is a kind of tropical subtropical teleconnection that we might be able to pick up at Hawaii. And although I'm not showing it here, there's been work that has been shown that the coupling or the strength of the teleconnections between the subtropics and tropics changes with PDO and probably changes with mean state. So we have this opportunity to look at kind of the state dependency of climate variability by looking at these corals in Hawaii. So that's just kind of some background. The next slide then goes back to that stage 11 plunge pool sample. So there's recent modern samples as well as the plunge pool stage 11 samples that we generated data for. This particular, what you can see here is that oxygen and carbon isotopes indicate that we're picking up the seasonal variability in the corals. And if you go to the next slide, it'll show it sort of in the context of yeah, just maybe show the whole thing now. So this is in the context of the plunge pool samples. So on the left, there's two samples, the modern samples, and then on the right, there's samples from the two plunge pools from stage 11. And the comparison the comparison between the modern and the stage 11 corals is what's illustrated here. What you can see really quickly to the eye is that the fossil samples from stage 11 have different mean values in strontium, calcium, oxygen isotopes, and that the other thing you can see is that the variability, generally speaking, is somewhat similar in terms of the amplitude, but there's this offset between them. So just a really kind of crude analysis or interpretation of this is that there's a hint that the sea surface temperature may have been different during stage 11, during this particular window within stage 11, and also that these corals are pretty robustly recording variations, very much like the modern samples. If you were to take the sea surface temperature, take the O18 and calculate the O18 of seawater that is implied by this data, you get an O18 of seawater calculation or estimate that is very consistent with other O18 of seawater estimates that are made in other ways, basically using sedimentary records. So there is a consistency there, and the relatively cold temperatures of these samples is also backed up by other records, not in Hawaii, because we don't have temperature records really from that area for stage 11, but in other parts of the Pacific, there's also slightly colder temperatures during this part of stage 11. So this showed us a number of different things, but mainly that these samples can be used pretty effectively to do paleoclimate, that the preservation is good enough for the dating and for the paleoclimate reconstructions, geochemical reconstructions. And obviously there's so many other things that we can throw at these samples in terms of analytical techniques and geochemical techniques to reconstruct paleoclimate in the past. So I'm just going to end it there, Jody, and I'll go back to you.
No worries. All right, so I guess I'll finish up just quickly here. As I said, it's quite a unique archive, and at the heart of this is its location, I guess, oceanographically, but also related to the rapid subsidence, which has produced this really, quite interesting, sequence of really expanded reef sections. And, we can get, as I said, based on the available data, and I should say there is a wealth, as I said, of samples and observations going back several decades by many workers, pulling a lot of the available information together to allow us to make these observations. And then just as a sort of a final point, in that sort of, through the gestation of this proposal, as I said at the very beginning, the strategy here is to use a seabed rock drill in contrast to what we did with Tahiti and Expedition 325. And as part of a proof of concept, our group has been fortunate enough to work on some fossil reef cores that actually were collected on the northwest shelf of Australia from shallower waters. These cores were collected in about 80 meters of water, and they were collected as part of a geotechnical study, but we were able to use them for sort of scientific purposes, but also to really illustrate. These are actually drilled with using a system called PROD, and it was able to recover a beautiful sequence fossil coral reef material, in many cases quite in very difficult, challenging environments. You can see these quite friable, altered grainstones and packstones, and it was able to do a really good job in these sorts of settings. So it bodes well for using a seabed rock drill for this sort of situation. So I'll just kind of end it there. This is a sort of a site map where we have our main areas off Hilo, Kohala, Kauai, Mahokono, and Kona. There's a whole suite of proposed drill sites, primary sites and alternate sites that look at a range of different depths and thus times, but also so-called wet and dry sides of the island. So this is part of the climatological aspects as well. And there's just a list here of the potential targets that are available. But I'll end it there, Dave, and hand it back to you.
That's great. Thanks very much, Jodie and Christina, for a super presentation. Let me just stop sharing. So yes, there's a couple of questions have come in already, but what we'll do is we're just going to park those for just now, and we'll carry on with the rest of the webinar to get the information across, and then we'll definitely come back to those questions and any others that might be posted during the remainder of the talk. So let me just share my screen again. Good. Okay, so let's move on now to the implementation of this expedition, which I've said has been run as a mission-specific platform expedition. So I'd like to now introduce Hannah Grant, who is the expedition project manager for this expedition. Hannah has been involved in our most recent expedition, that was expedition 386 in the Japan Trench, and there we used giant piston coring as the coring method. So Hannah has experience of coordinating an MSP expedition using an alternative coring method in multiple shallow holes. So Hannah will now give an overview of how this expedition will be run as an MSP expedition. So over to you, Hannah.
Thanks, Dave. Hello and welcome to everybody joining us today. So I'll begin this part of the webinar by explaining just what a IODP mission-specific platform is before touching on the expedition schedule. Then I'll talk about the platform itself and the drilling strategy we'll employ. I'll then talk about the standard measurements we'll take offshore and introduce a key part of MSPs, which is the onshore science party, and the activities that will take place there. And then we'll move on to the application process and the next steps for scientists who want to participate. So this expedition is being run, as Dave has said, as a mission-specific platform expedition, which means we will not use either of the two dedicated IODP vessels, the US-operated JOIDIS Resolution or the Japanese-operated Chiku, two vessels I'm sure that some of you will be familiar with. Instead, we will use a mission-specific platform, which is a vessel specially contracted to meet the unusual requirements of certain IODP expeditions, which can be things like working in very shallow water or ice-covered seas. In the case of this expedition, there is a need to core reefform material, which can have macro porosity and can be friable and loose, as Jodie showed. So standard API coring is not particularly suitable. To respond to this challenge, we are choosing to use a seafloor coring rig, which uses a smaller diameter bit and thinner kerf, which gives better results in these lithologies. And in addition, we have environmental and permitting constraints. And it has been recommended to us that using a seafloor coring rig is an appropriate way of working in a sensitive environment. And I'll give more information on that in a moment. So although MSPs and other IODP expeditions have several common elements, there are some key differences that you should be aware of. Before I go on to tell you about the expedition itself, I'd like to show you a brief outline of an MSP expedition. So first of all, our science party will be of the usual size for an IODP expedition. So around 30 scientists will form the science party. The expedition is made up of two parts, and the first part is the offshore phase. During the offshore phase, because accommodation and lab space is limited, we do not split the cores at sea, and we focus only on the essential and time-sensitive tasks, which are measurements of ephemeral properties, measurements required to guide drilling, and time-sensitive sampling such as microbiology. So around 8 to 12 scientists from the science party will participate offshore, so less than half, and candidates will be chosen based on the expertise needed to carry out these offshore tasks. If you apply and your application is successful, your invitation letter will specify if you are being invited as an offshore and onshore scientist or an onshore only scientist. So you will know at the invitation stage what your commitment to the expedition will be. If you wish, you can state on your application that you want to be considered for an onshore only position. That's absolutely fine. What you can't do, however, is apply for an offshore only position. So I'd also like to add at this point that there is no disadvantage to being an onshore only scientist. All data and sample information will be made available online for the whole science party to access soon after the offshore phase is complete. So following the offshore phase, phase 2 of the expedition is the onshore science party, which is held at the IODP Bremen Core Repository, where the cores are split and the full suite of IODP measurements, description and sampling takes place. So the whole science party, including those who sailed offshore, are expected to attend. The OSP, therefore, is more than just a sampling party compared to what sometimes occurs for the other IODP platforms. It is in fact equivalent to the main analysis that usually takes place offshore on the larger IODP vessels. So the key point here is that the expedition is both the offshore and the onshore phases together. At this moment in time, the offshore part of the expedition is scheduled for up to 60 days within a window that runs from mid-August to the end of October 2023, anticipating that it will start and end in Honolulu in Hawaii. If these offshore dates hold, as we expect, then the onshore science party will be held in Bremen in Germany for up to 4 weeks, starting in early 2024. And these exact dates will be confirmed in due course. We do hope to be able to include all expedition dates on the invitation letters, so everyone is aware of the commitment required before accepting the invite. So at the moment, in terms of the vessel, we are undertaking a procurement exercise to source a geotechnical vessel and a seafloor coring rig, with the vessel being large enough to accommodate our mobile science containers. This exercise is currently active, and due to commercial constraints, we are unable to present to you the exact seafloor coring rig and vessel that we will use. But I can say that the platform will be a geotechnical vessel similar to those that we have contracted previously. To give you an idea, this image is the DP Hunter that was used in Expedition 310 offshore of Tahiti in 2005. The Expedition 389 platform will be different in that we will not use a vessel-mounted rig like you see here. Instead, we will use a seafloor coring rig deployed via a launch and recovery system on the end of an umbilical. So these seafloor drills are deployed on the seafloor, as Jody showed, and essentially continuously core the entire borehole in one go over a period of a few days and store the cores on a carousel on the drill. After the borehole is complete, the whole rig is recovered to deck and the cores are unloaded by the drilling staff and the ESO curators before being passed to the science party for various initial analyses. There are several seafloor coring rigs that exist, and we're currently running a procurement exercise to secure a rig that will be similar to one of the examples that are illustrated here on the right. The coring bits and parameters can be varied depending on the lithologies being drilled, and the ESO drilling coordinators will work with the drilling contractors and the science party to select the most appropriate approaches. We will also carry a range of different bits and spares to cope with expected and also unexpected lithologies. So Jody and Christina mentioned the coring strategy in their presentation, but I shall reiterate that we are aiming to recover continuous reef records from the present day back to 500,000 years by continuously coring at up to 11 sites. The default position is to continually core a single borehole at each of the primary sites. However, depending on our success and the recovery we can achieve, the drilling strategy may be modified to react to our actual progress. We can never know exactly how an operation will unfold, but we will document our preferred strategy and any backup options in the expedition scientific prospectus, which is a description of the expedition that will be released a few weeks ahead of the offshore phase. So back up on deck, I want to give you a feel for the offshore environment and how we arrange MSP expeditions on unfamiliar vessels. The photo on the left was taken during our 2013 expedition in the Baltic Sea from near the rig looking down on the working deck. This is a customized setup and it is the hallmark of MSP expeditions. Being a temporary setup, the working deck is not as polished as other research vessels sometimes can be, but what it does offer is the flexibility to put whatever infrastructure we need on board to meet the expedition's objectives. On the right is the core bench where the recovered cores are taken out of the core barrels and prepared by the ESO curators. The cores then make their way into this configuration of blue containers that you can see in the left photo. These are the ESO containerized laboratories where the initial scientific analyses are carried out, and this is where the majority of the offshore work conducted by the science party takes place. The setup for this expedition will not be exactly like this, but it will be similar, and hopefully it gives you a feel for the offshore environment that you may find yourself working in. So the next photos I will show you are representative of the science area. So these images here are what is known as Main Street, which is basically 2 rows of ESO container labs facing onto a common walkway. The containers are arranged to follow the natural core workflows, so the whole cores and their subsamples can be easily transferred backwards and forwards from station to station in a logical manner. So looking into the containers, we can see the kind of working environment that scientists can expect should they become part of the offshores team. Here we have the curation van, the first point of call for the new cores arriving on the deck. We also have the petrophysics container with a multi-sensor core logger, a clean geochemistry lab for pore water analysis, and a core description lab with sample preparation facilities, microscopes, and computer terminals. We also have a clean microbiology mobile lab, which can be used if required. If space is too tight for all these container labs, then the geochemistry lab can double up as a microbiology lab. And finally, in the inset photo there, we can see the general science lab, which houses stations with microscopes, smear slide preparation facilities, and an area for sample description. So in terms of measurements, here is a list of measurements that are typically acquired offshore on MSPs. I explained earlier that the limited space and accommodation on most MSP platforms means we need to focus on high quality core recovery, some initial core description and capture of ephemeral, geochemical, microbiological, and physical property measurements. Due to the nature of sea coring rigs, we are unlikely to be able to accommodate downhole logging. However, we do own our own set of downhole memory tools that could potentially be used by our contractor on their seafloor coring rig. And that's a discussion that is ongoing as part of contractual discussions. So now I'd like to show a few photographs of the kind of non-lab general living spaces that scientists might expect offshore. Please bear in mind these photos are not from the actual vessel that we will use for Expedition 389, as they are from past expeditions, but hopefully they will show you the kind of thing to expect if you've never sailed offshore before. So on board, the accommodation will likely be basic, but functional and comfortable. Cabins are very likely to be shared, but we try to put people on opposite shifts to minimize disturbance when off shift. Here you see a typical eating area. We can accommodate special dietary requirements, and you will be asked to submit this information if you are asked to participate offshore. And then there's a typical relaxation area. These are good places to relax and chat to your fellow science party colleagues. And you will find various ways to keep yourself occupied when off duty. So leaving the offshore phase behind now. Because we can't do everything that we want to do offshore, we do need to have an onshore science party or OSP. The OSP is held at the IODP Bremen Core Repository at the Marham, University of Bremen, and here the cores are split open for the first time and the bulk of the core description and analysis is done. And in fact, most of the expedition science actually emerges here. The Marham has excellent labs and facilities to analyse the cores, and the whole science party must attend the onshore science party. So that's the 8 to 12 people who sailed offshore, plus the other 18 to 22 members of the science party. Participants will be accommodated in a local hotel close to amenities and restaurants with free tram travel provided between the hotel and the core repository. So this is a typical list of analyses carried out at the onshore science party. I'll let you read them for yourself. But what I will say is that the results from these analyses are published in the expedition report, which goes online 1 year after the onshore science party ends. And during that initial year, the science party have exclusive access to all the expedition data. And additionally, at the OSP, you will have the opportunity to sample for personal post-expedition research. This isn't actually the primary aim of the OSP, as the initial analyses will always take priority, but we have found that science parties can generally cope with analysis and post-expedition sampling at the same time. So I'll now hand back to Dave, who will discuss the application process and next steps. Thank you.
Thanks very much, Hannah. Good. So that concludes the implementation section of our webinar. Before we move on to the questions, and there's a few more I've built up there, I want to talk to you about the application process and what the next steps are. So if you haven't found it already, please visit this web address, iodp.org/expeditions/apply to sail. It will take you to the main IODP apply to sail page, and there you will find lists for all the current open calls on IODP. Also there you will find links to the various program member offices of IODP. So these program member offices, or PMOs, they coordinate the application process for scientists, and scientists should apply through the relevant program member office. So as well as submitting your application through your relevant PMO, I'd also urge you to ask them or check their website for information on participation support for this expedition. So the various PMOs, they offer widely varying levels of support to participate. The expedition will obviously pay for your accommodation and subsistence while you're offshore and while you're attending the onshore science party in Bremen, but all other costs must be paid by your local PMO or from other sources. So these other costs are things like travel to and from the ship and the onshore science party, any post-expedition grants to help you work on samples, travel to post-expedition meetings, and in some cases, salary compensation as well. So in a lot of cases, the PMO will pay for these costs, but in other cases, the PMO support can be limited, and then the applicant must find support from somewhere else. That's most likely to be from an external grant or from your institute. So please try and get that information from your PMO as early as possible, and that will help you to manage your participation. Okay, so what are the next steps? The application deadline is the 23rd of September, so that's 2 weeks today. After the deadline, the PMOs will assess the applications and they will pass us shortlists by the middle of October, so by the 17th of October. Then ISO and the coaches will review the shortlisted applications. We will also meet at the end of October to finalise the science party, and we will work with a view to selecting a science party based on expertise, but also nationality. So in terms of the kind of makeup of a science party, we're looking at 11 members from ECORD nations, 8 members from the USA, and 4 members from Japan. And then China, Korea, India, and Australia, New Zealand, they would get 1 each. So that'd be an additional 4. We also have additional science party positions that could be awarded to countries making an in-kind contribution. So far, that's not applicable to this expedition, but it's always an option, and that option can stay open virtually up to sailing date. So, all going to plan, we might expect invitations to be issued starting in November 2022, and those invites will be for offshore and onshore or onshore only roles. At that stage, we will send you an invitation pack, which contains extended information about the expedition. It would include everything from safety training and medicals to how to submit sample requests and how to request bringing any third-party equipment on board. So all scientists who accept the invitations and participate in the expedition will have the same rights and obligations. So just briefly, you'll have 1 year exclusive core and data access, and your main obligation is to publish your personal research in a peer-reviewed journal within 20 months of the end of the moratorium. And if you want more information on that, please look at the IODP sample data and obligations policy on the IODP website. Good, so I hope that was useful to you and it's given people an idea of what this expedition will entail. We'll now halt the presentations and we'll move to the questions, and there's a few there that we can look at. So I'll just stop the screen share just now and we'll open the floor for questions. Let's see what we have. Let's look first of all at the science type questions. I think most of them are science based. Yes, so first one here from Pankaj, I'm really interested to learn about MIS stage 67 from Hawaii, specifically the H2D reef in the original plan at 490 meter water depth. Are there similar analogues at these depths from elsewhere? Jodie, Christina, can you answer that one?
Yes. Are there similar analogues that, yes, is well developed? I'm not sure. Certainly we have age data that supports that ages, the age of that reef sequence of the H2 being that age. I guess, are you talking about other places in the world? There aren't that many examples of penultimate deglaciation reefs that are preserved. I think there are some records, actually, thinking about it, from the Huon Peninsula and sort of the uplifted reefs. So there are some examples that I can think of. Not sure if that answers your question, but
thanks, Jodie. Now, next one, do reefs respond in any way to the mixing of seawater with the active lava flows entering the sea nearby? In the modern reef isn't particularly well developed around the Big Island right now. Certainly we know that active lava flows or lava flows are, we can see them at the base of some of the reef sequences. In some cases, we can see clearly lava flows that have flowed out and draped over the top of the fossil reef sequences. So they clearly are interacting. It's entirely possible that some volcaniclastic sediments and also lava flows themselves could be interbedded within some of the reefs. Certainly that it's an interesting and complicating factor for this system. Yeah. Good, thanks, Jodie. Next one, are the reefs known to contain magnetotactic bacteria?
I'm not sure. Certainly, Christina, do you have any thoughts there?
I mean, no, I don't. I'm possibly, right? I mean,
yes, we know. Yeah, we know that microbialite sediments are clearly part of the upper parts of the reef sequences, the drown signatures. And we also know that there are significant microbialite crusts also within some of the shallower reef facies within the sequences that we have picked from ROVs and submersibles. So I would expect that is actually one of the goals of objectives of the expedition, is to really have a better understanding of the activity and influence of microbes in the framework building processes of the reef. So I don't know specifically in that case, but I would not be surprised if they did exist.
Yeah.
Thanks, Jodie. Christina. Now, next one, beside algae and massive corals, do you think you should be able to find larger foraminifera in the cores?
The answer is, yeah, there are definitely benthic forams within the fossil reef sequences that we have seen. So yes, they're a part of the reef sequence. There's shallow benthic forams as well as deeper sequences, depending on where you are in the facies.
Good, thanks, Jodie. Next one here, what evidence exists that the subsidence rate of Hawaii has been constant?
Yeah, good question. Indeed, that is based on a range of evidence. Now, over the last few 100,000 years, the available evidence from the reefs themselves, which have been dated, on different sides of the islands using uranium thorium. It tends to suggest around that rate. There's also dating of the volcanics, which also supports that. Certainly the strategy built into the proposal is to, for example, use the MIS 5E reef sequence, which is reasonably well understood as essentially a pinning point to try and better date and constrain that subsidence in different parts of the island. Because without a doubt, there is also there is a systematic tilting that is observed as a result of increasing load further to the southeast. So certainly that dealing with the subsidence and better constraining that subsidence is an objective of the expedition. But certainly what I would say is that compared with some of the other reef margins that have been worked on, which are from active tectonic, convergent margins, where we have, for example, meter scale co-seismic uplift events. That's why I use the term well behaved. Now, in the end, to reconstruct eustatic sea level, we need to understand subsidence, but there is a strategy to constrain that.
I'll just add something to that also, is that at least at the stage 11 corals that we looked at, we were able to generate an independent estimate of O18 of seawater, which can be related to sea level. So there's ways to triangulate possibly on this question as well.
Yeah, and then exactly right. And the other aspect, of course, is to penetrate into the basement. So dating the corals, getting some constraints from the basalts and interlaid flows, and a range of different methods.
Good, thank you both. Next one, what's the difference between drilling boreholes in multiple locations on a drowned reef versus drilling a single long borehole on the rim of an atoll? So I guess this comes down to the scientific reason, Jodie, why you went for the multiple hole approach.
Yeah, well, the way that the strategy is worked out is where we have sites that are picked to recover a core from each reef sequence, but in reality, we will more than likely drill multiple holes from a given reef. Where that's proven to be really powerful is this was demonstrated in the Expedition 325, where we're actually able to connect transects from a range of different cores to look at the relationship between shallow and deep coeval sequences, and that can only actually be done by drilling a transect of cores. And so we're going to do that in a sense by drilling these individual reefs that have grown through different glacial interglacial cycles. I think of that as a transect over that entire period, but we will more than likely drill multiple holes within a single reef. And that will do a number of things. It will allow us to potentially, for example, one of the sites is a what I call a double decker, where it actually has two terraces within that. So, we'll drill essentially multiple holes right next to each other, and that will also provide replication. And that was also useful in the event that perhaps we get a lack of recovery or drilling difficulties and so on. So the transect approach, is definitely has a lot of advantages than a single borehole.
Great, thanks, Jodie. I think we've got a couple of more kind of operational questions here. So are there instruments for rock magnetic analysis on board the vessel? So on board, Gunther, we have a multi-sensor core logger, and on there we have sensors for magnetic susceptibility. So that will be done on the whole cores at sea on the vessel. So that instrument is housed within the petrophysics container. That's all that will be done at sea. When the cores come back to Bremen, there's a chance for the paleomagnetists to take samples and run them through the instrument at the University of Bremen to take some initial PMAG measurements. And then the remainder of the PMAG analysis will be done post-cruise, post-expedition by the scientists in their home labs on further samples. So it's quite limited what we will do actually on board the vessel itself. Most of the PMAG will be done in Bremen and at the home institutes of the scientists involved. Next question is about pore waters. On board, pore water is usually done by squeezing. That would require opening the liner. Yes, it would if we had to do that. But given the cores will be lithified, might that be a challenge? Yes, it would be a challenge if the cores were hard. If there's any softer sediments that we have access to, they can be sampled using syringe rhizome squeezers that can pull the pore water out through the liner. That's our preferred method. But yeah, it's a judgment call that will be taken at the time, depending on what how lithified the cores are, whether we can actually take pore water out or not. But we have syringes, we have squeezers, so we can always remove pore water if it's possible to do so. And that
I would expect, yeah, Dave, that there will be sequences within the reef package where we would have, for example, unlithified sediments or volcaniclastic sediments, mixes of volcaniclastic and carbonate, where pore waters may be able to be extracted. Now that was the case, if you recall, from Tahiti. Not exactly the same setting, but more analogous, for example, than the Great Barrier Reef, where that pore waters were not really. I think there was some attempts, but there wasn't a lot to be had in that case. But with this expedition, I expect there could be possible.
Yeah. So we will be prepared for all eventualities, and we will work with our geochemist team in ESO and the co-chiefs, and also the invited geochemists to draw up a pore water program. Do the co-chiefs count towards the country allocation for participants? Not for MSP expeditions. So they do for JR, Joint Resolution expeditions, they do count, but for ECORD run MSP expeditions, they do not count towards the country allocation. So Jodie would not take an Australian place, and Christina would not take a USA place. Next one, will samples from the water column be collected as part of this expedition? So this is something we don't routinely do, but we have done in past expeditions. So if this is a requirement that you need specifically, then I would certainly mention it in your application as part of your proposed research. And when the time comes to submit a sample request and ask for third-party equipment to come on board, we can certainly look at that and try and build it into the operational program. My only concern about that might be that because we're using seafloor drills on the end of an umbilical, we will have equipment over the side connected to the ship with a cable, essentially, and the contractor might not be happy about having another piece of equipment on another cable being lowered at the same time. So we would have to look for opportunities to deploy equipment over the side to sample the water column when we aren't actually coring. So perhaps maybe when the drill comes back onto the deck and is getting turned around to go back again, there might be a window there where we could launch something and collect pore water. So it's certainly something that can be considered. And if you are interested in this, please mention it in your application. Good. A couple more now for science type questions. So in the modern time, we know global sea level is rising. Is this rising rate, is it a concern about today's coral growth? Jodie, Christina, do you want to take that one?
Yeah, I guess that's the issue of thinking about how high and how fast sea levels may get. I guess currently globally it's about 3 millimeters per year, but that rate could be up to 10 or 15, depending on what emission scenario we follow. If you take the current rate, you would say, based on known rates that reefs can grow, they should be able to keep pace with that. But I guess the other issue and concern is other environmental factors in combination with sea level rise that can act to stress and reduce the ability of the reefs to actually continue to grow vertically. And that's actually one of the key sort of questions or things that we can sort of ask and address in this expedition. Is we have a reef system that has grown in response to a whole range of different rates and magnitudes of sea level rise and temperature changes and other sorts of environmental changes. Ultimately, each reef does drown and is left behind. And so I hope we actually can learn a lot more about the environmental thresholds of these reefs into the past, or in the past, in response to different combinations and rates and amplitudes of environmental change.
Great, thanks, Jodie. Getting there now. When reefs get buried, is there a porosity change as a response to the burial?
I guess gross changes. I think for the most part they maintain, overall framework and structure. But of course, if we're talking about changes in porosity related to, say, diagenetic changes by secondary mineralization and secondary cements, these sorts of things, yes, they can be influenced by diagenesis. But if you're talking about sort of burial compaction and these sorts of issues, no, our experience with Expedition 310 and 325 is that we're not seeing those sorts of factors. These are, of course, deeper and maybe thicker packages, but we still expect to see reef framework, primary framework preserved. Not sure if that helps. Not sure I've done a good job of answering that one there, but
no, thank you, Jodie. That's good. Next question: what method is used for pore water pH? Now, that's a question I'm not personally able to answer, so I'm going to chance my luck, and I'm going to see if my colleague from Germany, who is our isogeochemist, is able to answer that question for us. Lucia Schneiders. She may or may not be available. Lucia, might you be there to answer this question?
Hi, Dave.
Oh, hi, Lucy. That's great. Thank you. Thank you for coming in at zero notice. Yes, did you catch that question there? It's about.
Can you repeat that, please?
Yes, I will do. Yeah. So the question was, what method is used for pore water pH?
We have an auto titrator unit where we have an electrode on. So we do pH and alkalinity in one run. First, we measure the pH that we need anyway, then later on to calculate the alkalinity, and then we titrate with a mild acid. I hope that sums it up.
Yeah, that's great, Lucy. Thank you so much for jumping in there.
You're welcome.
Yeah, thank you. Next one. Well, you mentioned magnetic susceptibility. What is the frequency and amplitude of the device that measures magnetic susceptibility? Can this be changed? Again, Gunther, I'm not a petrophysicist. I'm not able to answer that question. I'm just having a look online to see if there's another one of my colleagues who might be able to answer that. Let's see now. I think the only person that might be able to answer that is my colleague Simon. Simon, are you around and able to answer that one?
Yeah, hi, Dave.
Thank you, Simon.
Yeah, I'm as you know, and I'm not a complete expert on it, but yes, you can certainly change the settings that, and it takes it at different rates. So yes, so it is. Well, to cut a long story short, yes, you can change the settings to as you wish. Yeah.
Yeah. Thank you very much, Simon, for jumping in. Yeah, I did think that was the answer, but it's better that you answer that rather than me.
Sure.
Thank you. Okay, I think the last one here. Do you expect to be able to recover ensembles of multi-year coral sequences from the drilled cores in the same way that you were able to recover such sequences from the MIS 11 records?
Yes, I think we do. We're hopeful that we'll be able, certainly in that section, we were able to see, multiple massive corals overlapping each other So I think the expectation would be, and we've seen this in the Great Barrier Reef and Tahiti, where we would drill through sequence of a particular sequences of reef and particular coral assemblages, which are built by massive parietes. Massive parietes are one of the dominant reef builders. And we didn't mention here, there's also robust branching parietes, and another type of parietes called parietes compressor, which is also very common in the ROV and submersible samples. And we've also had, we didn't mention it here, but we've also had some success in reconstructing interannual climate signals from those corals also. And so again, the expectation or hope is that, yes, we will be able to do that. And of course, if we're able to drill another hole right next to that site, we may be able to get additional corals from the same time interval to get a whole range of different corals that might overlap. So that's an advantage of, in some cases, being able to do closely spaced holes, if that's within the scope of what we're able to do at any given site.
Thanks, Jodie. And another one coming here. Are the tides significant for formation of these reefs?
Well, I think tides are an important factor for any reef system. Depends on the amplitude and size of the tides in any area. I've worked with colleagues who work in the Northwest Shelf where they have macro tides of 5 to 6 meters. That's obviously an extreme example, but I guess the answer is yes, that they are important.
Great. That's super. Thank you very much. We've worked our way through those questions quite well. I do apologise that we've gone through the hour, but thank you for sticking around, everyone. I suggest that if there's any other questions that people maybe want to ask but haven't asked, they could either, if they're of a scientific nature, please contact Jodie and Christina directly and ask them the questions. If you have questions more on operations and logistics, please put them towards me and I will forward them on to the ESO team, who will be able to reply to you directly. So please, if you have any further questions before the application deadline, please don't hesitate to get in touch with the co-chiefs or the ESO team, and we'll do our best to advise you. Good. Thank you very much then. I think we'll leave it there. I'd just like to say thank you very much to Jodie and Christina for your science presentation. Thank you as well, Hannah, for your contribution today. And thank you also to my other ESO colleagues who chipped in at the end there. That is very much appreciated. And thank you also very much to all the scientists who have joined us today to learn about this expedition. I really hope that you all apply before 2 weeks' time to apply to join this expedition. We look forward to receiving your applications, and hopefully maybe one day we'll actually get to meet you face to face as science party participants as well. So we very much look forward to going through your application and to see what interesting science ideas and proposals that you might come up with that might enhance this expedition. Good. Okay. We'll leave it there. Good luck with your applications, and we'll see you soon. Thank you very much. Thanks, everyone.
Thank you, everybody.
Thanks, Jodie. Thanks.